Hi, good morning, students. I will just give a recorded lecture for root locus. Some of the students maybe can use it again whenever needed, even before the series or university exams. Okay, so root locus of first order system. So first order system, according to the first order or second order or third order systems, the root locus shape will vary. Even if the root locus is without a zero, if the transfer function is having no open loop zeros, and if there is an open loop zero, in that fashion also the root locus shape will vary. So we will just have a look on the general first order, second order systems, and third order onwards we have already done in the class. So first order system without zero are represented by the following transfer function, that is GSHS is equal to K over S plus alpha. So here you can see that the root locus of such system, this is like without zero, that is there is no S term coming in the numerator of the open loop transfer function, but there is a pole, only one pole, that is why it is termed as first order system, because the characteristic equation of this system will be S plus A alpha is equal to 0, where S to the power 1, that means it is first order. So the root locus of such systems like this systems, whatever may be the value of alpha can be starting from minus alpha, it will be, and alpha can vary from 0 to any number. So root locus of such systems is a horizontal line starting from minus alpha and moves towards minus infinity as k reaches infinity. So that this is the pole 0 map. So here only one pole, so minus alpha, and it is reaching, this is the root locus branch which is starting from alpha at k is equal to 0, and it is going towards the negative real axis towards as k tends to infinity. K, k is the system gain. K tends to infinity, its root locus will be, the branch of the root locus will be tending to infinity. So alpha different values I have given. Even here alpha 0, alpha 2, 1. Please try to just within 1 second you can draw this. Okay. And here you can see that instead of alpha it is 2, that means in this it is this point will be minus 2, that's it. And in the other case, the second case, it is minus 1, so that is minus of minus alpha, so it will be plus 1. So here it will start at this point and so on. It's very simple. Okay, so please do that. And in order for if you have a first order system with the 0, that is first order system with 0 are represented by the following transfer function, that is GSHS is equal to K into S plus beta by S plus alpha, where S is equal to minus beta is an open loop, 0 here. The previous pole is existing as such. So the root locus of such systems is a horizontal line starting from minus alpha, that is starting from the pole. Root locus always originates at a pole, and it has to end at a 0. If there are no zeros present, then it will end at a 0 at infinity. That is what it is happening. So root locus of such systems is a horizontal line starting from minus alpha, that is minus alpha, and moves towards minus beta as k reaches infinity. And these things you can do as a homework, as I told you before. So you have to work out, because you are going to write the exam. Okay. And root locus of second order systems now. So the second order system without 0, that means there is no pole, no 0 means there is no S term in the numerator, but which has 2 poles, that means that is why it is second order, S to the power 1 into S to the power 1. When you expand, you will get a square. And the 2 poles are located at minus alpha 1 and minus alpha 2. So the root locus of such systems are vertical lines like this. This is whatever may be the values, that is a thing. So minus alpha 1 to minus alpha 2. So that depends also the values, how big it is. So here we have taken alpha 1 as the magnitude of alpha 1 is less than magnitude of alpha 2. So that is why if here alpha 1 is, say for example 1, then it is minus 1, this is 2, minus 2. So in between there is a breaking happens, and because you know that the root locus branch will start like this. Okay, like this is the arrow. If you want, it is you can put even the arrow also. So as these two root locus branches starting at minus alpha 1 and at minus alpha 2 are coming face to face, it has to break at some point in between alpha 1 and alpha 2, and as it breaks we have to find also the breakaway point. So this is the general criteria. Then as there are only 2, you will get as 90 degree. Okay, so that is the thing. So please try to do these. These are the same like S into S plus 2 without 0, and having 2 poles means the characteristic equation will be of second order. And the root locus with the second order system with 1 0, that is k into s plus beta by s plus alpha 1 into s plus alpha 2. The such systems are either horizontal lines or circle also. It can be circle also. We have done an example in the class. Depending on the pole 0, the values, that is if it can be like depending on the beta value, whichever it is greater. So if the beta or the 0 is existing in between alpha 1 and alpha 2, so it is greater than alpha 1 and less than alpha 2, then it will be like this. That is here, this one starting from minus alpha 1, it will end here, and here it is minus alpha 2, it is going out. Okay. And if it is the beta is the maximum, like the 0 value is greater than alpha 1 and alpha 2, it will be the root locus will be a circle. So that is here it will start, both the root locus starts, and at this point it will break away, and this breakaway will break away at this point and break in at this point will happen. These type of problems we have worked out, and even the derivations we have done. Okay, and if beta is the smallest, that is comparing with alpha 1 and alpha 2, beta is the smallest, then the root locus will be like this. Sorry, like this. That is, it will start at minus alpha 1 and it will end at one of the branch will end at the open loop 0, that is available at minus beta. And here the other root locus branch will start at minus alpha 2 at k is equal to 0, and it will go towards infinity. So these shapes you just remember, so that depending on the values, the same system, but depending on the values, the shape of the root locus branches will be differing. So please you have to note that these things we have done in class already. Just do it, like here I have put as A and B. Do it again, in the sense if you didn't do when I am doing in the class, then you have to do it. Okay, as homework it is given. Try, and if you have a doubt, you can just WhatsApp me. I will reply for that. If you have a doubt or you are not getting the branches or something like that. Okay. If you apply all the rules, or the 8 rules, it will be ready. The root locus will be ready to that. And we will now move on to, and here under second order I told you, third order onwards we have done in the class already. So third order onwards it is not like we cannot just like that give the shape and so go. It's not like that. So here actually I have given a fourth order system. So this is again the same question is asked. Even it is a worked out question in Anand Kumar, and it is asked in K2 December 2018. That is your super seniors batch. That is I think the first KTU batch. That is in December. They were in S7 December 2018. Their exams. And this question K over it is actually you have to draw the complete. This you see example 6.17. Draw the complete root locus for the system with GSH is equal to K over S into S plus 6 into S square plus 4S plus 13. So the same question is asked. Okay. So you have to draw so starting with the initial values or initial rules. So initial first step is you have to find, here you can see that there are no open loop zeros. So m value, the small m value will be equal to 0. By seeing this system we can write that here m is equal to 0. And you have to find the open loop poles. So the open loop poles, there are 4 poles, because here s is equal to 0 is a pole, s is equal to minus 6 is another pole, and the solution of s square plus 4s plus 13 will give you 2 poles, because it is a second order polynomial. So that you will find as s is equal to minus 4 plus or minus root of b square, that is 4 square minus 4ac, 4 into 13, that is 52 divided by 2. So that will end up with minus 2 plus or minus j3. Therefore, n is equal to 4. You can see that all the number of open loop poles in the given open loop transfer function is 4. But there are no open loop zeros, that I told you. So the number of poles will be equal to the number of root locus branches. That is always it is the case. And here, as there are no zeros, n minus m branches at infinity. So that is, you will have n minus m asymptotes, where m is the number of zeros. So all the root locus branches will originate at the open loop poles. So at s is equal to 0, when k is equal to 0, it will originate. At s is equal to minus 6, at k is equal to 0, again the root locus branch will originate. And also at these complex poles, that is at minus 2 plus j3, at k is equal to 0, it will originate, and also minus 2 minus j3, at k is equal to 0, it will originate. So that the initial step is to, you have to draw the poles and zeros if there is a zero. Now in this example there are no zeros. So initially you have to draw like this I have drawn, and when you draw the root locus, even for the series test or for the university examination, you have to draw it in a graph paper. Otherwise there will be errors. When you draw, you are not taking this into scale, it will be having problems. So that is why you have to draw the root locus always in a graph sheet. If you are having a lab record, I think the lab record is there are graph sheets in that. Otherwise you can buy it. It's very less, only 1 rupee or so. I think 1 rupee 2 graph sheets or something like that. So if you can, you have to, when if the for the series also, if the question is there for drawing the root locus, you have to, if you draw in a graph sheet only, you will get the credits for the graph. Or if the root locus is correct also, if you are drawing just in a paper, you will not get credit, because there may be some error and even the shape may vary due to this. So for university exams, usually the KTU, the university will provide the graph sheets for the control system paper. Even the semi-log sheet also they are providing, because for the frequency response that we have to do in module 4, that will Bode plot. For drawing the Bode plot, we need the semi-log sheet. Now the graph sheet should be needed. So even for the series test that you are going to write on this 4th of December, if there is a question of plotting of root locus, you must draw in a graph sheet. So that it will be having accurate branches, like the points, everything. If even the angle I told you can measure using a protractor. You can have a scale, and here I have given all the root locus branches with a different color. This is actually red color. I do not know, when I take the picture it is showing something else. Then also it is, there are 4 different colors is put for 4 different branches. There are 4 branches because there are 4 poles coming. Okay. So all the root locus branches will start at the open loop poles at k is equal to 0. That I have clearly written. At k is equal to 0, this branch will start. K is equal to 0, here also this branch will start, and k is equal to 0, this branch will start, and k is equal to 0, this branch will start, like this. So as you can see that this is the initial step. After that we will I will explain the rules. Okay, already I have explained, just this is a recorded lecture for those who didn't get it. Okay. So the complete root locus is drawn. That is what I have shown. So it is drawn by means of taking the rules. That is, first rule is the root locus will be symmetrical about the real axis, because the pole zero location is symmetrical with respect to the real axis. So we have seen already the root locus is symmetrical. And the 4 branches of the root locus start at the open loop poles at s is equal to 0, s is equal to minus 6, s is equal to minus 2 plus j3, and s is equal to minus 2 minus j3, where k is equal to 0, and terminate at the open loop zeros at infinity. So as there are no zeros, if there is a 0%, it will terminate at that finite value. As here in this example there are no zeros, all the root locus branches will end or terminate at the open loop poles at infinity. That is, it will 4 asymptotes will be there. That is when k is equal to infinity. Okay. And here for the third rule, that is the 4 branches of the root locus go to the zeros at infinity. That is along the asymptotes, making angle theta q. And this theta q, you can see that here you can the theta q, you are finding it as theta q, the formula we have already done, 2q plus 1 by 1 into pi by n minus m, where pi is 180 degree. So this q is from 0, 1, 2, 3 etc. up to n minus m minus 1. Here n minus m is 4. You know that the number of poles is 4 and number of zeros is 0. That means n minus m becomes 4 minus 0. So that is 4. And n minus m minus 1. Q is 0, 1, 2, 3 only then, because 4 minus 1. So 0, 1, 2, 3. You put 0 here. Okay. You will get it as, if you put 0 there, you will have, if you 0 there, you will have 1 into pi, that is pi by 4. if you are putting phi is equal to 1, then the next asymptote angle, that is 3 pi by 4, and that is 3 into 180 by 4, then 5 into 180 by 4, and 7 into 180 by 4. So that you will have these angles as 180 by 4, you know that it is 45 degree, so 45, then the 135, 225 and 350. This is the in degrees, because you are drawing using a protractor and you are using the in degrees only, the angle. Okay, but the point of intersection of the asymptotes on the real axis, that is centroid, by definition you know that it is actually negative. So sigma in the negative real axis, sum of real parts of poles minus sum of real parts of 0. So sum of real parts of poles, you can see that it is minus 6 is there is a pole at minus 6, so minus 6, and these two poles, that is minus 2 plus j3, it is having a real part minus 2, again minus 2 minus j3 is also having a real part minus 2, so that is added, so you will get minus 6 minus 4 minus 10 by 4, that is minus 2.5. So minus 2.5 you will have the centroid, that is the meeting point of these four asymptotes at the real axis. So here, that is what here it is drawn, that is you can see that this in pencil I have drawn, you can see this one, this point is minus 2.5. So this is this is 1, 2, 2.5. Okay, so this point is 2.5, and at this minus 2.5 all the four asymptotes will meet with the creating that angle. This angle will be 45, this angle will be 135, this angle will be 225, and this is 350. Okay, so like that you will have the angle of asymptotes and the meeting point, that is a centroid, at the point. So the root locus exists wherever the root locus exists, that also we can see here, that I have already explained the rule, that is here on the real axis where the root locus will exist, because here there is a pole and here there is another pole. If we take any of the point in between 0 and minus 6, you can see that to the right of that point, if a point I am considering here as P, then to the right of this point there is a total number of poles and zeros is 1, which is an odd number, that means that the Rex is a root locus branch. But if I take a point here, you can see that the total number is 2, which is an even number, so there is no root locus branch at this point. Even here also, here on the real axis, if I take to the right of this, there is 0 number of poles and zeros. That means it is an even number, so there will not be any pole, any root locus branch that is existing. Only here, that means again the root locus branch at k is equal to 0, it will start or originate from this pole 0 and it is coming towards this pole minus 6. And here also the root locus branch at minus 6 will start at k is equal to 0 and it is coming towards this. That means these two root locus branches on the real axis are coming face to face. So it has to break at some point. So at this point it is breaking, and it has to move like this. Why? Because the asymptotes are parallel lines to the root locus branch. So the root locus branch and the asymptotes will meet at infinity. Yes, they will meet at infinity. That means they are parallel lines. So after the breaking, you have to draw the root locus such that it is in a parallel fashion to this. So if at this point you have to find where it will break. So somewhere in between 0 and minus 6 it has to break. So where it is breaking, by the rule, the dk by ds is equal to 0. That is, the breakaway points on the real axis is to be found by dk by ds is equal to 0. That you know that dk by ds, so the magnitude condition, or if from the characteristic equation you know that it is 1 plus GSHS is equal to 0, or GSHS magnitude is GSHS is equal to minus 1 you will get, and the magnitude will be equal to 1. So the magnitude of GSHS that is given in the question, the GSHS question is this one, that is k over s into s plus 6 into s square plus 4s plus 13. Here that is, okay, that is equal to 1. And just you cross multiply k is equal to, and expand it, you will get it as s to the power 4 plus 10s cube plus 37s square plus 78s. This we will get if you just take out the bracket, expand it, multiply it. Okay. Then do dk by ds is equal to 0. That solution will give you the breakaway points. There will be 3 breakaway points you will be getting but you can see that only 1 is valid there. So here when you do the dk by ds, that is derivative with respect to s, you are doing s to the power 4 will be 4s cube plus 10 into 3, 30 s square plus 74 plus 74, yes, because 2 into 37 plus 78 is equal to 6. So just take the solution. This solution is very easy. You can put it in the calculator for the equation. In the calculator you will get the values of s as s1, s2 and s3. You are getting it as s as minus 4.1, then minus 1.65 plus or minus j 1.386. So you can see that one breakaway point is complex. So that is not actually the complex breakaway point, that is where it is minus 1.65 plus or minus 1.65 is somewhere here, and here there will not be a breakaway point is possible. So as there is no root locus branch in this fashion, so only valid breakaway point is minus 4.1, and this 4.1 you have to, the root locus have to break on the real axis, that is it is in between 0 and minus 6. You know that minus 4.1 is in between 0 and minus 6. So what you can do is, after this breakaway point only you can do, so this root locus branch is finished. Okay, that is this is coming like this, that is 2 root locuses reaching at the point minus 4.1 and breaking up. And then you have to find the complex pole angle of departure. So the root locus branch start at this complex pole, but the angle of departure of complex pole you have to find, not like on the real it will be always on the 180 degree face only. But here how will you find? We have that phasers you have to draw, that is these phasers, this one phaser is this is the second phaser, and this is the third phaser. That is, we are considering the angle of departure of this complex pole. So the angle made by, or the angle contribution by all other poles and zeros. So all other poles and zeros you will have the other poles as, if you are considering minus 2 plus j3, you will have minus 2 minus j3 as other pole. Another pole is equal to 0 and another pole is equal to minus 6. So angle made by that other poles towards this pole. So that's what we are finding. So the theta d1 is 180 plus phi, where phi is the angle contribution by the other poles. That is phi, all the phi will be now negative. Why? Because all are poles. So numerator angle minus denominator angle. So numerator angle is 0. So here theta 1 is the angle made by this pole, s is equal to 0. And theta 2, I have taken it as the angle made by minus 2 plus minus j3, and the angle made by minus 6 as theta 3. So minus of theta 1 plus theta 2 plus theta 3, so that will be equal to what theta 1 is. You will get it as, like, how will you find this theta 1? And if for using, if you want, you can use protractor otherwise. You can find it as, this is 90 degree and you have to add this angle. So this angle, you know that if you take tan, isn't it? Tan inverse of this angle will be tan inverse of opposite side by adjacent side. This opposite side, you know that is 2, isn't it? Divided by the adjacent side, this is 3. So tan inverse 2 by 3, you will get it as almost, I think, 90. Here you have already 90. Okay, 90 plus 33.6. So it is 123.6. This angle, that is theta 1. Then theta 2. Theta 2, you know that it is, of course, it is a complex conjugate. So it is making an angle of 90 degree. It is 90. Okay, right angle triangle, 90 degree. And this one again you can find tan inverse of opposite side by adjacent side. Opposite side is here 3, isn't it? This is 3. And adjacent side is here minus 6 and this is 2, that is the difference is 4. So tan inverse 3 by 4. So that will be obtained as 36.8. So you have to add these 3, that is phi is minus of this full combination, that is 123.6 plus 36.8 plus 90. So you will get as minus 250.4. And this 250.4, we will just take it as, round it as 250 itself, no need for the decimal, because we are going to take 180, like 180 plus phi, where phi is minus 250. So you will have minus 70 degree. So theta d1 is 70 degrees. So some small manipulation, or if you do some rounding, it may end with 71 also. It doesn't matter, it is 70 you can take. In the textbook and all it is given 70 itself. So 70 degree is the angle of departure for this pole minus 2 plus j3. So similarly theta d2, that is due to the angle of departure at minus 2 minus 3 will be negative of this. So that is minus theta d1 and minus, it will be minus of minus 70, so it is plus. It is plus 70. So plus 70. That is why it is plus 70. Okay. So it will be plus 70. So that is how you will do. So now only the angle of departure you have found. Now after it is angle of departure 70, you can start. How it will end? So it will go like this. We know, because you have an asymptote here. But as there is a j omega axis in between, you should find the angle of intersection. The point of intersection at the j omega, on the j omega axis of this root locus branch. So the point of intersection can be found from the root array. So that we have already studied. So that's what is done. So 1 plus GSHS is equal to this one. We have explained already this one. So already finished. And the angle of departure also I have done in the graph sheet itself. So 1 plus GSHS is equal to 0 is the characteristic equation. From that you will get the characteristic equation as this. From this you can form the root table and find the point of intersection of the root locus on the j omega axis. So here when you do this, you will get the values like k, and here it is 29.2 into 78 minus 10k. So here, if this s to the power for the stability of, for the system to be stable, all the elements in the first column of the root array must be positive, so that it should be k should be greater than 0, and this term also should be greater than 0. These are all greater than 0, like these are all positive. So here the range of value of k for the system to be stable will come as k less than 227.76 and k greater than 0. So the critical value or the marginal value of k, we will say it as 227.76. So that this km, that is the marginal value for k to be stable, k stability for the system. So for k greater than 227.76, the system has poles in the right half, thereby making the system unstable. So how will you find the marginal stability? Means it is on the j omega axis. Okay, that is if it shifts to the right hand side, the system will become unstable. So here you can write as 29.2 s square, that is you have to form the auxiliary polynomial. So here if you have this as 0, that is a full row 0, s to the power 1 row 0, at what value of k? When 29.2 into 78 minus 10k is equal to 0. For that value is, that k value is 227.76. If you put 227.76 here, you will get here 0. Okay, and so the just previous row will form the auxiliary equation, that is 29.2 s square plus k is equal to 0, where k you have to put this 227.76. That's what is done, and from that s square is equal to this we are getting minus 7.8. Square root of minus 7.8 is will have a j term, that is plus or minus j 2.8. So the point of intersection of the root locus branch on the j omega axis is going to be 2.8 j, and this point of intersection, that is j 2.8, through that only this root locus branch will go, and finally it should be this asymptote and this branch should be in parallel. That means they will meet at infinity. So the root locus branch is go on increasing towards infinity when k tends to infinity. This branch also, it is go on increasing to infinity, is go on to when k tends to infinity. So here we can see that this is the root locus plot, and the point of intersection is 2.8 plus or minus j 2.8. There is a point of intersection at plus j 2.8, and also the other branch is the point of intersection is minus j 2.8. Hence the frequency of sustained oscillation, actually we will say s is equal to, you are putting for the frequency domain analysis, s is equal to plus or minus j omega, where omega is 2.8 radians per second. So this is the final root locus, the full-fledged root locus branches, as well as the root locus, we will say, for the system given GSHS is equal to K over S into S plus 6 into S square plus 4S plus 13. So please do by your own, by listening to this recorded lecture, and if you have a doubt, please WhatsApp me or call me. Okay, and that finishes that question. So here the similar questions I have given again KTU December 2019. You can see that K over S into S plus 4 S square plus 4S plus 20. You see that the same type it is. It is also like fourth order. There is a complex pole here. There is a pair of complex pole here. Here there are two real poles also. The same thing that we have here. Like only thing is the values are different. So I mean to say that if you have like this, you will proceed with the same, but you may not get the same shape of the root locus branches. You see, this is the root locus branches for this one. As these values varies, that is 6 is varied to 4, and this values varies, it is going to change. You see, the entirely different shape it is obtaining. Okay, so that is why. So this is another. That's just your seniors question. Last year pass out students. That is December 2019, 2020 pass out batch has returned, KTU. So you see the same type of question. So that is what for the higher order systems, fourth order onwards, we have to draw it only. Under second order, you can have even with the values, that the shape will vary, that I told you. Maybe it can be circle and all. So here, this is the answer I am showing you. This is the answer final plot. A final plot is not just the answer, okay? Because you have to you have to apply all the 9 roots for the root locus branch, for the root locus construction, then only you will end up with this. Before this, there are 2 pages or 2.5 pages that you have to write for finding all these values. Okay, the phasor angle, the asymptotes, the point of intersection, that is sigma, then the angle of departure, the point of intersection on the geometric axis, the breakaway point, etc. So all these things you have to see, okay, then only you have to draw the root locus. And when you draw the root locus, please draw like this, okay, that is like this in the sense in the graph sheet. You must draw in the graph sheet. Those who are not drawing in the graph sheet will not get any mark, even for the university as well as for the series, okay. And here again similar case, this is somewhat similar to the other one. That is K over S into S plus 2 into S square plus 2S. This also you can try. That is why I am showing it in the recorded lecture. So these things are for you, it is given. So you can just pause it and see what is the answer. Just take this question, try to do it in a graph sheet, and finally you can check the result. That is the idea. Here also the another homework. Okay. So this also you just do, and here it is asking at what value of K the system becomes unstable. So that is that value when the K value is having, when the one of the row, that is S to the power 1 row becomes 0, and you are forming the auxiliary polynomial just prior to that row. And at this point of instability, determine the frequency of oscillation. The frequency of oscillation we have told for the example, this one I told you. The frequency of oscillation, this one, this is 2.8 radians per second, that is obtained at the critical value or the marginal value of K for stability. Okay, so these things you have to. This is also a final answer I have put. Okay, see the shape is again different. Okay, it is in the just a mirror image of what we have done now. So according to the values here, that will differ. This is also a fourth order system. Okay, so please try to do it. I think after this, these things I have done, that determine the breakaway and breaking points. This we have done in the class, I remember. Just DKVDS is a solution that we have already done. We are doing it on each and every day. So this short recorded lecture, please go through this before you come to the class tomorrow. Okay. So today actually we didn't have a class. Okay. So there will be some small portions, maybe I may say. And all these things are there for the series, okay, in the sense the portions for the second series is module 3 and module 5 full. Module 3 is this root locus, root Hurwitz, and small frequency domain specifications are there that I may say it tomorrow. And the module 5 we have already completed, that is module 5 is the state space analysis of the continuous time system. Module 6 we have covered, but that is only jury stability is pending, but that will not be there for the series test. You have module 3 full and module 5 also full. Okay, module 6 maybe you have to study for the university. Okay, thank you students. Please listen to this recorded lecture and then come to the class. Okay.